You are settled into a quiet seat aboard a small spacecraft, drifting through the darkness between the stars. The cabin lights are low, the air is still, and a soft electronic hum wraps around you like a distant lullaby. Outside the window, two familiar shapes travel together, Earth, bright and blue, and the Moon, pale and calm. Tonight, you explore Earth and the Moon from space, and you follow one gentle question all the way through the dark. How did these two worlds become a pair, and how do we know what we know when we look at them from so far away? You can let that question float lightly, without needing to hold it tight. From this distance, Earth looks like a living marble. Sunlight glances off oceans and scatters through clouds, and along the edge you can sometimes imagine a thin, tender glow where air becomes space. It is easy to forget, from the ground, that our atmosphere is a delicate skin, with most of its weight pressed close to the surface. The blue you see is not paint or magic, just physics in a quiet disguise. Air molecules scatter shorter wavelengths of sunlight more efficiently than longer ones, so the daylight sky leans blue, and that tint can soften the whole planet from far away. Over oceans, the surface itself is dark, and clouds provide the bright white contrast. The Moon, by comparison, is a world that keeps its secrets in plain sight. Its colors are subtle, charcoal plains, lighter highlands, and crisp shadows inside old craters. Without a thick atmosphere to blur the view, sunlight and darkness meet sharply there, as if someone drew a line with a careful hand. One of the first mysteries people noticed is that the Moon always turns the same face toward Earth. Night after night, the same pattern of dark patches returns, familiar as landmarks on a map. Scientists now call this tidal locking, a slow gravitational settling that made the Moon's rotation match its orbit. You can picture it like a gentle tug that repeats, again and again, until wobble becomes quiet routine. Over long time, gravity raised bulges in the Moon's shape, and the constant flexing lost energy as heat. The end result is a stable alignment, like a key finding the groove it fits best. Long before spacecraft, people tracked the Moon as a natural calendar in the sky. Its changing shape, from thin crescent to bright full disk and back again, helped structure months and seasons for farmers, sailors, and storytellers. The pattern feels like transformation, but the underlying geometry is simple and steady. Half of the Moon is always lit by the sun, just as half of Earth is always in daylight. The phases are the changing angle between the sun, the Moon, and your viewpoint on Earth, which decides how much of that sunlit half you can see. The crescent is not a shadow on the Moon, it is a turn of the spotlight. Sometimes, the geometry becomes even more precise, and an eclipse arrives. A lunar eclipse happens when Earth's shadow falls across the Moon, and the lunar surface can take on a coppery tone as sunlight filters through Earth's air. A solar eclipse happens when the Moon slides between Earth and Sun, briefly covering the bright disk. It is a quiet coincidence that the Moon and the Sun appear close to the same size in our sky. The Sun is vastly larger, but it is also vastly farther away, and those two facts balance for us on Earth. That balance is why total solar eclipses can happen, with a dark circle edged by a delicate halo. To turn the Moon from a symbol into a measured world, humans learned to gauge its distance. By comparing the Moon's position against background stars from far-apart locations on Earth, a method called parallax, astronomers could work out how far it was. The average comes out to roughly 240,000 miles, a gap spacious enough for many Earths. On some nights, when the Moon is a thin crescent, you can faintly see the dark side glowing. That is Earthshine, sunlight reflected from Earth, bouncing gently onto the Moon and back to your eyes. Even before satellites, it hinted that Earth is bright and cloudy, a world that sends light outward into space. When telescopes arrived, the Moon's face changed from smooth perfection to rugged terrain. Galileo sketched the Terminator and noticed shadows that suggested mountains and crater rims, using geometry to estimate heights. The moon became a physical place, not a polished sphere, and that shift opened the door to thinking of Earth as one world among others. A little later, Isaac Newton tied the whole scene together with a single idea: the same gravity that makes objects fall also guides the moon's path. An orbit is like a continual fall that keeps missing the ground because the world is curved away beneath it. With that, Earth and Moon became a problem you could calculate, not just admire. From our spacecraft, you can feel how much of space science begins with simple brightness. Scientists use the word albedo for reflectivity, the fraction of sunlight a surface sends back. Fresh clouds have a high albedo, dark oceans a low one, and the moon sits somewhere in between, its dusty soil scattering light in a soft, matte way. Even from this ship, you can sense that Earth and Moon are not just neighbors. They tug on each other constantly, and you feel that connection on coastlines as tides rise and fall. The moon's gravity pulls more strongly on the near side of Earth than the far side, stretching the oceans into gentle bulges. As Earth rotates, shorelines pass through those bulges, and the water level changes in a rhythm that human life has learned to expect. The sun also contributes to tides, and when sun and moon line up, the tides tend to be stronger. It is a daily reminder that gravity is not an idea but a shared force. Earth itself is a planet of motion, turning on its axis while it travels around the sun. From space, you can watch the boundary between night and day, astronomers call it the terminator, slide across continents and oceans. Every sunrise and sunset is a simple shadow line on a spinning sphere. The idea that Earth is round was not born from rockets. Sailors watched ships sink hull first over the horizon, and travelers saw different stars at different latitudes. In ancient Greece, careful thinkers used geometry and shadows to estimate Earth's size, finding a number close to about 25,000 miles around. From this window, you can also imagine Earth's shape more precisely. It is not a perfect sphere, but slightly flattened, wider at the equator than pole to pole, because rotation adds a small outward push. Satellites measure this shape with exquisite care, because even tiny differences matter for mapping and navigation. Earth seasons, too, are a story written in geometry. The planet's axis is tilted, about 23.5 degrees, so sunlight falls more directly on one hemisphere and then the other as Earth orbits the sun. Winter and summer are not about distance from the sun, but about angle and daylight. Here is a gentle connection: the moon helps keep that tilt relatively steady. Earth's rotation axis wobbles over time, like a slow top, and the moon's gravity adds stabilizing influence. Computer simulations suggest that without our large moon, Earth's tilt might vary more wildly over long spans. To see these truths from space, scientists rely on light and timing, not intuition. Cameras measure brightness in different colors, including wavelengths your eyes cannot see, such as infrared that tracks heat. Radios and lasers can measure distance and motion with astonishing accuracy, turning invisible relationships into clear numbers. The moon teaches in another way: it preserves history. With no global oceans, no steady rain, and no active plate tectonics reshaping the surface, many ancient features remain visible for billions of years. Each crater is like a timestamp, recording an impact from the early solar system's busy days. Earth erases and rewrites its surface more often. Wind and water wear mountains down, rivers build deltas, and plates of crust drift, collide, and sink. That recycling is part of what makes Earth habitable, because it helps regulate carbon dioxide over long times and renews nutrients for the oceans. From above, Earth's clouds are not just decoration. They are part of a heat engine, moving energy from warm regions to cooler ones and reflecting some sunlight back to space. Modern satellites watch cloud cover, sea surface temperature, and ice, helping scientists understand climate as a system of flows. Another invisible shield surrounds Earth, a magnetic field generated deep inside. In the outer core, molten iron and nickel flow and twist, and because the material conducts electricity, it can sustain a magnetic dynamo. That field guides charged particles from the sun toward the poles, where auroras glow. The moon does not have the same kind of global magnetic shield today. Yet some lunar rocks are magnetized, hinting that the moon once had a stronger internal magnetic field long ago. Even in silence, stone can remember, and scientists listen to that memory with careful instruments. All of this sets the stage for a deeper question that puzzled scientists for centuries: where did the moon come from? Early ideas ranged from the moon forming alongside Earth, to Earth capturing a wandering body, to the moon spinning off a fast-rotating young Earth. Each idea tried to fit what people could observe. The leading picture today is called the giant impact hypothesis. In the early solar system, growing worlds often collided, and one hypothesis is that a Mars-sized body met the young Earth in a glancing encounter. Material lifted into orbit could have gathered into the moon, while Earth slowly settled and cooled. Even that story has open details, and scientists are careful about what is certain. The broad idea fits many clues, but researchers still debate the exact angle of impact, how much material came from each body, and how the system mixed afterward. In science, a strong explanation can still keep a few quiet mysteries. One reason the story is testable is that rocks carry fingerprints. With radiometric dating, scientists measure how unstable atoms slowly change into stable ones at known rates, like a natural clock inside minerals. Lunar samples brought to Earth show ages around 4.5 billion years, close to Earth's own ancient beginnings. From the ground, the moon can feel like a lamp. From space, it becomes a companion world with geology, highlands made mostly of lighter, older crust, and dark maria that are plains of hardened volcanic basalt. Those plains formed when lava once flowed and filled huge basins, then cooled into rock. In the moon's dark patches, you see a record of heat escaping from a small body. The moon is smaller than Earth, so it lost internal heat more quickly, and its volcanic era faded long ago. Earth's larger size helps it keep a warmer interior, feeding plate tectonics and volcanism today. There is another quiet experiment still running between the worlds. The moon is slowly drifting away from Earth as tides transfer energy and angular momentum, a change measured at about 1.5 inches each year. Scientists can detect it because laser light is bounced off reflectors left on the moon's surface, and the return time is tracked with great care. That kind of measurement feels almost like listening for an echo in a canyon. A pulse leaves an observatory on Earth, crosses the space between worlds, and returns with a tiny delay that carries meaning. Over years, the pattern reveals the moon's changing orbit and Earth's subtle flexing under tidal forces. Now, let your attention drift back to the quiet cabin for a moment. The ship's systems keep a steady temperature, and tiny thrusters make gentle corrections you can barely feel. Outside, the Earth and Moon hang in the window like two chapters of the same book, bound by gravity. In the coming parts of this journey, we will follow the tools that let humans truly see from space. We will visit early telescopes and careful measurements, then the first spacecraft that photographed the moon's far side, and the missions that carried instruments, astronauts, and samples. Each step adds detail without taking away wonder. For now, it is enough to hold a simple picture. Earth is a world of water, air, and restless change, wrapped in a thin layer where life thrives. The moon is a quieter archive, its surface preserving deep time in cratered stone. Together they form a system, like a pair of dancers keeping time. You do not need to memorize anything tonight. You can simply listen as ideas pass by like constellations, bright for a moment and then fading gently into the dark. The most important thing is the feeling of scale, and the calm truth that you are part of this view. As the ship glides on, the stars stay steady and unbothered. Earth's blues and whites turn slowly, and the moon keeps pace in its long orbit, always returning, always familiar. If your eyes are closed, you can still picture them there, and let your breathing find the same slow rhythm. You remain in the small spacecraft, where the lights are dim enough that the window feels like a second room. The hum of the cabin is steady, like a quiet breath. Outside, Earth turns slowly, and the moon keeps its patient distance. Tonight, we lean into how humans learn to see this pair not with imagination, but with instruments. Before anyone left the ground, people watched from rooftops and fields, letting the moon's face become familiar. Telescopes sharpened that familiarity into detail. Shadows near the terminator revealed cliffs and crater rims, and careful observers drew maps by hand. Still, half the moon stayed hidden, always turned away, a simple mystery that waited. In the middle of the last century, rockets began to climb high enough to photograph Earth's curve. The images were grainy and brief, but they carried a new feeling: the sky was not a ceiling. Even when the pictures were taken for practical reasons, they quietly changed what "up" could mean. Then came the first artificial satellites, small and persistent, circling above the weather and the birds. When Sputnik began to beep in 1957, it was more than a sound, it was proof of orbit. An orbit is free fall that never reaches the ground, because the ground curves away underneath. Those early beeps were tracked by timing and direction, by listening stations spread across the planet. From simple radio signals, scientists learned where a satellite was, how its path shifted, and how Earth's thin upper air could slow it. Even in spare data, there was a gentle lesson: space is measurable. Soon, satellites carried sensors instead of just transmitters. Explorer 1, launched in 1958, helped reveal a region of trapped radiation around Earth, later called the Van Allen belts. The discovery was a reminder that Earth is surrounded by invisible structure, shaped by its magnetic field and the sun's breath. When you look at Earth through the window, those belts are not visible. But you can imagine them as faint, broad arcs, guiding charged particles along magnetic lines. Understanding them mattered for spacecraft design and for human safety, yet the science itself remained quiet and elegant: fields and particles in motion. In 1960, a satellite named Tyros 1 returned early television images of Earth's clouds. The pictures were soft by modern standards, but the message was clear. Weather was not just local, it was planetary. From above, storms became spirals, and cloud bands traced the circulation of air and heat. From there, it was natural to turn outward, toward the moon. The Soviet Luna program began with fast flybys and hard lessons. Luna 2 struck the lunar surface in 1959, becoming the first human-made object to reach another world. A few months later, Luna 3 photographed the moon's far side. The far side was not a new world in the sense of fantasy. It was still rock and dust and craters. But seeing it for the first time completed the moon's face, like turning a familiar stone in your hand. Scientists noticed fewer dark maria there, and more highland crust, hinting at a different internal history. To bring back those first views, engineers relied on telemetry, the art of sending measurements over radio. Signals carried tiny shifts that could be turned into images, temperatures, and voltages. It was like learning a new language, where a faint pattern in noise could become a picture of a cratered plain. Across the ocean, the United States sent its own early lunar missions. The Ranger spacecraft were built to dive toward the moon and take photographs until impact. In the mid-1960s, Ranger 7, 8, and 9 returned thousands of close images, revealing that the surface was covered in fine debris. That debris has a name: regolith, a layer of broken rock and dust made by countless impacts. You can think of it as a history book ground into grains. Each meteorite strike shattered and mixed the surface, and without rain or rivers to sort it, the regolith stayed where it fell, spread by tiny shocks. After imaging came the careful step of landing. Surveyor landers touched down softly, testing whether the moon would hold a spacecraft or swallow it into dust. Their footpads sank only a little. Cameras showed small rocks, shallow trenches, and a surface firm enough to bear weight, which eased a nervous question. The Soviet Union achieved its own soft landing with Luna 9 in 1966. Later missions placed rovers on the surface, and some returned samples to Earth. Each success was quiet in its own way, because the most important result was not a headline, but a new piece of physical evidence. You can sense, from this calm distance, that exploration is often an accumulation of small certainties. A temperature reading here, a soil test there, a sharper photograph, a better map. Step by step, the moon became less like a symbol and more like a place with terrain, chemistry, and time. All of that led into the Apollo era, when the moon shifted from distant target to reachable destination. The Saturn V rocket lifted spacecraft from Earth with a force that is hard to picture, yet the journey itself was mostly coasting. After a brief burn, the craft would fall toward the moon under gravity's patient pull. On the way, astronauts navigated with stars and mathematics. They used inertial systems to keep track of rotation, and they checked their position against known star patterns through sextants and optics. Mid-course corrections were small, gentle pushes, because in space, tiny changes made early can become large changes later. Apollo 8 was the first crewed spacecraft to orbit the moon, in late 1968. As they passed behind the lunar limb, radio contact dropped away, and the silence was complete. Then, from lunar orbit, they saw Earth rise over the gray horizon, a bright, cloud-wrapped sphere in a black sky. That image, later called Earthrise, did not add a new equation. It added a new perspective. From far away, Earth looked whole and fragile, without borders or labels. It is the kind of view that makes arguments feel smaller, not because problems vanish, but because the context grows. A few months later, Apollo 11 carried humans to the lunar surface. The landing site lay in a smooth dark plain called the Sea of Tranquility. The first steps were careful, almost slow, because they were also tests: how the dust behaved, how the suit moved, how a human body felt in low gravity. What mattered most for science was not the footprint itself, but the samples and instruments. Rock fragments and core tubes went into sealed containers. Experiments were placed on the surface to listen for moonquakes and to measure the flow of heat from below. Practical work, done with calm hands. Over the next few years, more Apollo missions expanded that work. Apollo 12 landed with greater precision. Apollo 15, 16, and 17 carried a small rover that let astronauts travel farther from the landing site, collecting rocks from different layers and visiting the rims of larger craters. Many of the most ancient lunar rocks are anorthosites, light-colored stones formed when a molten early moon separated, with buoyant minerals floating up to form crust. Darker basalts from the Maria record later volcanism. Breccias, which are rocks made of broken pieces fused together, speak of impacts and shock. Back on Earth, laboratories dated these samples using radioactive clocks. The numbers, translated into years, pushed researchers toward a moon that formed very early, close to the beginning of the solar system. Some samples also showed that the moon and Earth share strikingly similar isotopic signatures, a clue with sharp edges. That similarity became part of the ongoing puzzle about origin. If the moon formed mostly from another body, why does it resemble Earth so closely in certain isotopes? If it formed from Earth material, how did the impact work physically? Science held the options gently, adjusting models as data accumulated. Another long-lived gift of Apollo was laser ranging. Astronauts placed mirror-like reflectors on the moon's surface. Observatories on Earth send laser pulses toward them and measure the return time. From that timing, scientists can track the moon's distance with extraordinary precision, and watch it drift outward slowly. The same measurements help test gravity itself, because they track the moon's orbit with such care. They also reveal tiny motions of the moon, called librations, which are small wobbles that let us see a little beyond its average face. Even a seemingly fixed world has subtle movements. When the Apollo era ended, the moon did not become forgotten. Orbiters continued to map its surface, improving our understanding of gravity variations and topography. Decades later, missions like Clementine in the 1990s and Lunar Prospector suggested hydrogen near the poles, hinting at water ice and shadow. Near the lunar poles, some craters never see sunlight because the sun stays low on the horizon there. These permanently shadowed regions can be colder than any natural place on Earth. In that deep cold, water molecules delivered by comets or created by solar-wind interactions can remain trapped for a long time. Evidence for lunar water grew in the 2000s, through orbiters and impact experiments. In 2009, the LaCrosse mission guided a spent rocket stage into a shadowed crater while instruments watched the plume. The data indicated water and other volatiles mixed with the excavated material. Around the same period, the Lunar Reconnaissance Orbiter began returning extraordinarily detailed images and maps. Its camera could reveal small boulders and narrow tracks, and its laser altimeter traced the moon's shape with fine accuracy. The moon's surface, once a blurred disk, became a world of measured contours. Other nations also returned to lunar exploration. Japan's Kaguya orbiter, India's Chandrayaan missions, and China's Chang'e series each added new perspectives and new instruments. Different orbits, different wavelengths, different questions, all layered onto the same quiet globe of rock and dust. When China's Chang'e 4 landed on the far side in 2019, it did so with the help of a relay satellite, because the far side cannot see Earth directly. The rover, Yutu-2, rolled slowly across ancient terrain. Its pace matched the moon itself, unhurried, enduring, observant. While the moon was being revisited, Earth was being watched continuously. Satellites like Landsat, beginning in 1972, recorded changing forests, coastlines, and cities. Instruments compared the greenness of vegetation, the warmth of the sea, the brightness of ice, building a long record of our home as a system. You can think of those records as a kind of planetary diary. Each orbit adds another line, another glance at clouds and land. Over years, patterns emerge, drought and recovery, melting and refreezing, cycles of dust and smoke. The view from space turns change into something you can measure gently. To make sense of these images, scientists talk about resolution, the smallest detail an instrument can separate. From far away, a whole continent can be 1 pixel. From closer in, a river becomes a line, then a shape, then a textured surface. Detail is not just clarity, it is a choice about scale. In our own quiet window, you are seeing Earth and Moon at a scale where they look simple. Yet you now know that simplicity is layered over enormous complexity. Instruments and missions do not replace wonder, they refine it. They let you admire not just beauty, but the processes that shape it. If you listen closely, you can imagine the old signals still traveling, long dispersed into space. The beeps from Sputnik, the faint tones of telemetry, the crisp clicks of cameras sending lines of light and dark. They are not preserved as sound in the void, but as radio waves fading outward. The deeper lesson is that exploration rarely arrives as a single revelation. It arrives as patience. A blurry cloud image becomes a climate dataset. A distant lunar disk becomes a map, then a landing site, then a handful of rocks with ages written inside them. The mystery narrows, but it does not end. As we drift here, Earth's night side turns toward us, and city lights shimmer like scattered embers beneath clouds. The moon remains quiet, reflecting sunlight without complaint. In the next part, we will lean closer to what those rocks and measurements say about the earliest days, when both worlds were still forming. For now, let your mind rest in the steady rhythm of orbits. The ship keeps its gentle course, and the window holds its calm view. You can let the history of missions settle like dust in low gravity, slowly, without urgency, while your breathing stays soft and even. You are still in the small spacecraft, where the quiet is so complete that even your own breathing feels like a soft instrument. The cabin lights stay low, and the window holds its steady view. Earth turns with slow confidence, and the moon follows, pale and watchful, as if keeping an old appointment. As you look, your mind can drift backward in time, not in fantasy, but in evidence. Scientists reconstruct beginnings the way you might reconstruct a calm evening from a few remembered sounds. They use chemistry, physics, and the scars on stone to sketch what happened when Earth and Moon were young and still settling into themselves. Long ago, before oceans and forests, the solar system was a disk of gas and dust around a newborn sundae. In that disk, grains collided gently and stuck, then grew into pebbles, then into boulders, and finally into bodies large enough for gravity to pull more material in. Accretion is simply that patient gathering. In those early days, the inner solar system was crowded. Many worlds were only partly formed, like rough drafts. Their paths crossed and recrossed, and collisions were common, not as sudden violence in a story, but as the natural result of many bodies sharing similar lanes around the sun. Earth began as one of those growing bodies, built from countless impacts that delivered rock, metal, and heat. Each collision added material and also energy, warming the interior. Over time, dense metal sank toward the center, forming a core, while lighter rock moved outward. Differentiation is the name for that sorting by density. Even now, through the window, you can imagine Earth's layers as a gentle structure, a metallic core, a thick mantle of slowly flowing rock, and a thin crust where continents rest. The layers are not stacked like shelves. They are the outcome of melting, sinking, and cooling, guided by gravity and time. The moon's layers are simpler, yet they carry a deep history. Lunar samples suggest that early on, parts of the moon were molten, forming what scientists call a magma ocean. As that melt cooled, certain minerals crystallized and floated upward, creating a light crust. The bright highlands you see are part of that ancient buoyant skin. So how do you get a moon in the first place, one large enough to stabilize tides and paint eclipses onto Earth's sky? The leading idea is the giant impact hypothesis, which says that a young Earth collided with another large body. That body is sometimes called Theia, a name used as a placeholder for an object we infer, not one we know directly. In this picture, the impact was not a head-on crash, but a glancing meeting, like two spinning stones brushing at speed. The collision would have thrown hot material into orbit around Earth. That orbiting debris, mostly rock and vapor, could have gathered into a disk, and then clumped together, cooling into the moon. It is a calm thought to hold. The moon may be the child of a ring. Rings are not only around distant planets. For a time, Earth may have worn one too, made of glowing rock fragments. Under gravity, those fragments would have collided, stuck, and built a single body, smoothing itself into a sphere as it grew. Scientists test this story by checking whether it matches what they can measure today. The moon's relatively small iron core, compared with Earth's, suggests that much of the metal had already sunk into Earth's center before the moon formed. That fits a scenario where the moon formed mainly from mantle-like material, not from dense core metal. Another test comes from the system's angular momentum, the shared spin budget of Earth's rotation and the moon's orbit. Any origin story has to account for how fast Earth turns and how the moon moves today. Models of giant impacts can reproduce that balance, though the details depend on the exact angle, speed, and mixing during the collision. Then there is chemistry, which is like a signature written in ratios. Many elements come in different isotopes, atoms with the same chemistry but slightly different mass. Earth rocks have distinctive isotope patterns, and lunar rocks often match them closely. That similarity is one reason the moon feels like family, not a stranger captured from far away. At the same time, that similarity raises a quiet puzzle. If the impactor contributed much of the moon's material, you might expect the moon to look chemically different. To resolve this, some models suggest the collision mixed material thoroughly, blending the impactor and Earth's outer layers into a common reservoir before the moon condensed from it. When you hear mixing here, you can imagine a vast, hot atmosphere of rock vapor surrounding the early Earth, with turbulence stirring it like wind over a warm sea. This is not a scene you need to picture sharply. It is enough to know that, in physics, heat and motion tend to erase sharp boundaries, especially right after an energetic event. Other researchers explore variations, an impact that spun Earth faster, an impactor with a composition already similar to Earth, or a sequence of smaller impacts instead of one. The science remains active. The broad outline is strong, but the exact script is still being edited, line by line, as new measurements sharpen what is plausible. From the window, the moon looks serene, but its face is full of impact scars, and those scars are part of the next clue. By counting craters and comparing them to dated samples, scientists can estimate the relative ages of different terrains. Older surfaces collect more craters, like a quiet patio gathering dust over time. The oldest lunar highlands are heavily cratered, suggesting they formed early and then endured a long reign of impacts. The darker Maria, smoother and less cratered, formed later, when lava flooded giant basins. Those basins themselves were made by impacts, and the lava arrived afterward, filling the low places when the moon still had enough internal heat. Earth's early surfaces are harder to read, because Earth keeps remaking itself. Plate tectonics recycles crust, and water and air weather rock into soil. That is why the moon is so valuable. It preserves a record of solar system events that Earth has mostly erased. The moon is not just a destination, it is an archive. One chapter in that archive is sometimes called the Late Heavy Bombardment, a proposed period when impacts were more frequent than usual. The idea comes from clustering of ages in some lunar samples and from crater counts. Scientists still debate the exact timing and intensity, and some prefer a more gradual decline instead of a sharp spike. However it played out, impacts mattered because they delivered energy and sometimes volatile materials, including water-bearing compounds. On Earth, water also likely came from multiple sources, including the original building blocks and later deliveries. The details are still studied, but the result is clear in your mind: oceans became stable enough for chemistry to grow complex. Once Earth cooled enough to hold a crust, water vapor condensed into rain, and rain gathered into basins. Over long time, carbon dioxide was drawn down by weathering and by burial in rocks, helping regulate temperature. These processes are slow, steady, and self-correcting in a way that feels almost like breathing, though they are purely physical. The moon, smaller and drier, followed a different path. Evidence suggests it had volcanic gases and perhaps brief episodes of surface water in the far past, but it did not maintain oceans. Without a thick atmosphere, it could not keep heat or water near the surface for long. Its story is mostly written in stone and shadow. Even so, the moon is not completely dry today. Water ice and other volatiles can hide in cold traps near the poles, and a thin exosphere of atoms drifts above the surface. Solar wind carries hydrogen that can interact with lunar minerals, creating hydroxyl and water-like signatures in some regions. These are subtle processes, but they are real. Now let your attention return to the spacecraft for a moment. The ship is a small bubble of warmth in a vast cold, and that contrast is part of what the moon teaches. Without air, temperatures swing strongly between sunlight and shadow. On Earth, the atmosphere and oceans smooth those swings, sharing heat around the globe. From space, you can see that smoothing in the way Earth's night side is not uniformly cold. Clouds trap some warmth, and oceans release stored heat. On the Moon, nighttime is deeper and more complete, because there is little to hold onto heat. The same sunlight falls on both worlds, yet their responses are entirely different. The difference shapes their surfaces. On Earth, wind and water round edges and carry sediments, and living things alter chemistry in quiet ways. On the Moon, micrometeorites and radiation slowly darken and garden the regolith. A sharp crater can remain sharp for ages, its rim preserved like a careful etching. Still looking outward, you may wonder what the Moon has done for Earth beyond tides and beauty. Tides may have helped stir early shorelines, mixing nutrients and concentrating chemicals in cycles of wet and dry. Scientists discuss this gently, because life's origin is not fully known, but it is reasonable to say the Moon's pull shaped Earth's coastal rhythms from the start. The Moon also slowed Earth's rotation over long time. As tides dissipate energy, Earth's spin loses a little speed, and the Moon gains a little orbital energy, drifting outward. Early in Earth's history, days were shorter. Over hundreds of millions of years, the day lengthened toward what you experience now, a pace suited to circadian life. Those changes are not dramatic in a human lifetime, but they are real on geological scales. Coral growth bands and ancient tidal sediments on Earth can record day length in the distant past, offering an independent check on the story told by laser ranging. Separate lines of evidence, like separate stars, can point to the same direction. Another shared feature is the way both worlds respond to impacts. A large impact on Earth can trigger climate effects for a time, but Earth's atmosphere and oceans help it recover. On the Moon, an impact simply adds another crater to the archive. The same event has very different consequences depending on the world's ability to buffer change. If you imagine the giant impact again, it helps to remember that giant is relative to embryos, not to modern Earth. The early inner solar system contained bodies of many sizes. Some were as large as planets in the making. The collision that formed the Moon, if it happened as the leading model suggests, was part of that normal process of sorting and merging. Scientists run simulations to explore which collisions can produce a Moon-like satellite. These are computational experiments, where gravity, heat, and fluid motion are modeled step by step. The results are compared to lunar geology and chemistry. The simulations do not give a single answer, but they narrow the range of stories that can fit the evidence. The evidence itself keeps improving. New analyses of old Apollo samples, and new samples from later missions, refine isotope ratios and mineral ages. Instruments become more sensitive, and questions become more precise. This is one of the quieter truths of science: discovery is often not a new object, but a new decimal place, handled with care. From your seat, Earth and Moon are a pair suspended in darkness, and it is comforting that their origin can be approached without certainty turning into arrogance. Scientists speak in probabilities, in best fits, in models that explain many observations at once. Uncertainty is not failure here. It is the honest shape of knowledge when you look far back in time. As the spacecraft drifts, you can let the early solar system feel less like a chaos and more like a slow settling. Gravity pulled scattered matter into organized orbits. Heat drove melting and separation. Time allowed surfaces to cool and atmospheres to form or disappear. In that long calm process, Earth became a home, and the Moon became its companion record. In the next part of our journey, we will stay with the evidence but move closer to what the Moon's surface reveals in detail: the basins, the lava plains, the polar shadows, and the subtle chemistry of dust. For now, you can rest with a simple thought: the Moon's quiet face is the cooled edge of a once molten beginning, still circling Earth with steady devotion. You are still in the small spacecraft, and the window is your quiet classroom. The cabin hum stays low and even, and outside the glass the moon's surface looks almost close enough to touch, though you know it is far. Earth glows nearby, soft with cloud and ocean, while the moon holds its details with crisp patience. As the ship drifts, you notice how the moon changes when the sun's angle changes. When light arrives from the side, shadows stretch and the landscape becomes readable, like a relief map. This is why scientists love the terminator, the boundary between lunar day and night, where every ridge and crater rim casts a clean, honest line. In full sunlight, the moon can look flatter, because shadows hide. But near the terminator, a small bump becomes a long shadow, and the eye can measure height without touching anything. Early lunar cartographers used this trick with telescopes, and modern orbiters still use it with cameras that watch the same ground under different lighting. From above, the moon is a mosaic of circles, and each circle is a story of an impact. A meteorite arrives fast, strikes without warning, and excavates a bowl, throwing rock outward in a bright spray. The moon's lack of thick air means even small objects can reach the ground, and the surface records them like a patient diary. If you were standing there, you would not see new craters forming often. Most days on the moon are quiet. Yet across long time, countless tiny impacts churn the ground, and that slow churning is called gardening. It mixes the regolith, the powdery layer of broken rock, into a deep blanket that covers almost everything. Regolith is not like beach sand. Its grains are sharp, fractured, and sometimes glassy, made by impacts that melt and shatter stone. Apollo astronauts described it as clinging and stubborn, because the grains can carry electric charge and because there is no wind or rain to round them smooth. From orbit, it looks soft, but it is a complex material. Woven into that dust are larger fragments, scattered like pebbles on a dark path. Some are pieces of ancient crust, bright and plagioclase-rich, formed when the moon's early melt separated and floated lighter minerals upward. Those bright highlands, especially on the far side, are the moon's oldest visible skin. The darker plains, the Maria, are younger in comparison, though still ancient by human standards. They are made of basalt, lava that once flowed across low basins and cooled into smooth rock. The Maria formed mainly on the near side, and their dark color creates the familiar patterns you recognize from Earth. That near side and far side difference is one of the moon's quiet mysteries. The far side has fewer Maria and a thicker crust, while the near side shows more volcanic flooding. Scientists connect this to differences in crust thickness, internal heat, and the way Earth's gravity may have influenced early lunar cooling, but the story is still being refined. When you look closely, you can see bright streaks radiating from some craters, like pale spokes on a wheel. These are ray systems, thrown out when impacts excavate fresh material and scatter it far. Over time, space weathering darkens them, so rays are often signs of relative youth, a fresh mark on an old face. Space weathering is slow, subtle change driven by micrometeorites and the solar wind. Tiny impacts melt grains into glass, and charged particles alter the chemistry of the surface. The effect is to darken and redden lunar soil over time. No storm does this, no wave, just the steady touch of space itself. To turn these textures into knowledge, orbiters carry more than cameras. Spectrometers split reflected sunlight into colors, including infrared, and those colors reveal minerals, because different crystals absorb light in different ways. From spectral fingerprints, scientists can map basalt, anorthosite, olivine, and many other ingredients without lifting a single rock by hand. Other instruments listen for different signals. A neutron spectrometer can sense hydrogen by the way cosmic rays knock particles from the ground. Radar can probe roughness and, in some cases, hint at ice in permanently shadowed regions. Gamma-ray measurements can reveal elements like iron, titanium, potassium, and thorium spread across the surface. As you float here, Earth's brightness makes the moon's subtle tones easier to appreciate. The moon reflects only a small fraction of sunlight compared with Earth's clouds and oceans. That low reflectivity is why the lunar surface often looks gray rather than white. In the quiet of space, gray becomes a rich palette. One of the most dramatic lunar features is not a crater you recognize by name, but a basin so large it shapes an entire hemisphere. The South Pole Aitken Basin sprawls across the far side, a vast ancient scar. It is so old that later impacts have softened its edges, yet its size still matters for understanding the moon's deep interior. Basins like this can excavate material from great depth, bringing up clues about the mantle beneath the crust. Scientists search basin floors and ring structures for exposed minerals that would not appear at the surface otherwise. Each patch of unusual composition is a whisper from deeper layers, carried upward by violence long ago and then preserved in silence. Gravity mapping adds another layer of whisper. The moon's gravity is not perfectly uniform, because mass is not distributed evenly. Dense basalt fills some basins, and thick crust or buried structures change the pull slightly. By tracking tiny changes in a spacecraft's orbit, scientists can map these variations, turning motion into a picture of hidden mass. In the early days, those gravity anomalies surprised mission planners. Some spacecraft in low lunar orbit behaved unexpectedly, as if tugged by unseen hands. Later studies connected these anomalies, sometimes called mascons, to dense material beneath Maria basins. What felt like misbehavior became a clue about the moon's internal structure. Inside the moon, there is still activity, though it is gentle. Seismometers left by Apollo recorded moonquakes, some triggered by tides as Earth's gravity flexes the moon, others by thermal changes, and some by impacts. The quakes can ring longer than earthquakes because the moon is dry and fractured, and vibrations fade slowly. From these signals, and from measurements of rotation and gravity, scientists infer that the moon has a core, likely with a solid inner part and a fluid outer part, though smaller than Earth's and cooler. The moon is not dead stone. It is a cooling body, still adjusting, still settling into its shape. The polar regions add a different kind of story, written in temperature rather than rock type. Near the poles, some crater floors never receive sunlight. They remain extremely cold, and in those cold traps, water ice can persist. The idea of ice on the moon once seemed strange, but the physics of shadow makes it plausible. What counts as water on the moon can be subtle. Some is ice in shadowed pockets. Some is hydroxyl bound to minerals, created when solar wind hydrogen meets oxygen in lunar rocks. Some may be delivered by comets or trapped from ancient volcanic gases. The amounts differ by place, and scientists measure carefully, refusing to oversimplify. From orbit, you cannot see ice directly with your eyes in most cases. Instead, you see its effects in data, changes in reflectivity at certain wavelengths, hints in neutron counts, patterns in radar reflections. It is a good lesson for the mind at bedtime. Not everything real is immediately visible, and that is fine. The moon's poles are also interesting because sunlight can graze some ridges almost constantly, while nearby craters remain in deep shade. This creates neighbors that are both very warm and very cold within a short distance. For future explorers, that contrast matters, because you can imagine solar power and ice resources living close together. While the moon holds stillness, Earth keeps moving in the window. Clouds swirl, oceans glint, and the thin atmosphere softens the edge. Earth's surface is shaped by water and plate tectonics, processes that erase old impacts and build new landforms. From space, you can sense that Earth is an active conversation, while the moon is a preserved archive. Yet even Earth carries traces of impacts, though they are harder to see. Some ancient craters are buried or worn down, and some are visible only through unusual rock structures or gravitational hints. Comparing Earth and Moon reminds you that absence of evidence is not always evidence of absence, especially on a planet that recycles its surface. The Moon also teaches about time through crater counts. If you know the rate at which impacts happen, you can estimate how long a surface has been exposed. Scientists calibrate this method using samples with known ages from Apollo and other missions. It is not perfect, but it is a powerful way to turn patterns into timelines. When you hear rate here, you can let it be gentle and approximate. The impact environment changes over billion-year spans, and the smallest craters can be erased by later gardening. Scientists include uncertainties and compare multiple datasets. In good science, confidence grows from agreement among different methods, not from a single tidy number. Look again at the lunar Maria, and you can imagine their basalt cooling in slow sheets. Some flows formed wrinkles and ridges as they contracted, leaving long sinuous shapes. In places, lava carved channels, like frozen rivers. These are not wet valleys, but they are still rivers of history, traced in rock. In other places, you can see winding, shallow depressions called rills. Some may be collapsed lava tubes, where molten rock once flowed beneath a crust and later drained away. Others may be channels cut by flowing lava. Each rill is a reminder that the Moon once had a warm interior active enough to reshape the surface. There are also domes, low rounded hills that can mark gentle volcanic eruptions. They rise subtly from the plains, easy to miss unless the sun angle is right. Again, the terminator helps. Light from the side turns a nearly invisible swell into a readable shape, and the Moon becomes a land of quiet contours. The far side holds its own wonders beyond its thicker crust. There are crater chains, strange swirls, and the immense impact basins that dominate its geology. Some swirls may be tied to magnetic anomalies that protect the surface slightly from solar wind, leaving lighter patterns. They look like brushstrokes, but they are physics. As you rest with these details, the spacecraft remains steady, and the stars do not move. You can let the Moon's surface become a calming pattern rather than a puzzle to solve. Still, a gentle curiosity can stay awake. Why did volcanic flooding favor the near side, and what does that say about heat inside the Moon? Scientists look for answers in heat-producing elements. Elements like potassium, thorium, and uranium release heat as they decay, and maps show that some of these elements are concentrated on the near side in a region sometimes called the Procellarum Creep terrain. This enrichment may have influenced where volcanic activity persisted. Creep is a shorthand built from potassium, rare earth elements, and phosphorus, components associated with late-stage lunar magma ocean chemistry. It is not a magical substance, just a geochemical label. Yet it carries meaning, because it hints at how the Moon's early melt evolved and where certain materials collected as it cooled. All these maps and inferences combine into a new kind of view from space. You are not only seeing shapes, but also compositions, temperatures, and hidden structures. The Moon becomes layered, a visible surface, a subsurface hinted by gravity, and a chemical story inferred from light. It is a world understood by many senses, not just sight. Earth, too, is mapped in layers by space instruments. Infrared sees heat, microwave instruments can sense moisture, and spectroscopy can track gases like carbon dioxide and methane. These measurements are not only for curiosity. They help people understand weather, climate, crops, and the changing face of land and sea. In the quiet of your ship, you can hold both worlds at once, the Moon as a preserved record, Earth as a living system. The contrast is soothing rather than sad. Earth's changes include growth and recovery as well as loss, and the Moon's stillness includes beauty and clarity as well as barrenness. Each world is what it is. As the ship continues to drift, the line between lunar day and night slides slowly across a familiar cratered field. The shadows lengthen, then soften, then disappear into darkness. You can let your thoughts do the same, lengthening into curiosity and then easing back toward rest. In the next part, we will widen the view again and connect this lunar archive to the larger story of Earth's habitability and the way sunlight, gravity, and chemistry weave together. For now, stay with the simple comfort of observation. You are safe in the dim cabin, watching two worlds keep their quiet orbit together. You are still in the small spacecraft, where the lights are turned down to a gentle glow and the air feels softly filtered. The ship does not hurry. Outside the window, Earth and the Moon share the same black background, two bodies in the same frame, reminding you that space makes relationships visible. When you watch them together, it becomes natural to stop thinking of them as separate objects and start thinking of them as a system. A system is just a set of parts that affect one another, trading energy and motion back and forth. Earth and Moon trade in tides, in spin, in reflected light, in long, slow stability. From far away, Earth's brightness can feel like a simple fact, but it is the result of balance. Sunlight arrives, some is reflected by clouds, ice, and pale deserts, and some is absorbed by land and sea. The absorbed energy returns as heat, glowing in infrared, and the planet stays temperate by matching what it takes into what it gives back. The atmosphere is the quiet mediator in that exchange. Certain gases, including water vapor and carbon dioxide, interact with infrared light and slow the escape of heat. This is the greenhouse effect, and it is not a trap so much as a blanket. Light comes in easily, warmth leaves more slowly, and the surface stays warm enough for liquid water. You can imagine that blanket from this seat. At the edge of Earth, the air is not a thick wall, but a thin blue curve, faint and tender. Most of it lies close to the ground, pressed down by gravity. From orbit, you can understand why small changes in composition matter, because the whole atmosphere is, in a sense, a shallow ocean of gas. Clouds complicate the story in a soothing way, like a lullaby with harmony. They reflect sunlight, which cools, and they also hold in heat, which warms. Their net effect depends on altitude, thickness, and location, and that is one reason climate science leans so heavily on satellites, which can watch cloud patterns day after day. Some of those satellites are like patient librarians. They do not chase drama. They record sea surface temperatures, ice coverage, vegetation greenness, and the height of the sea, building long histories one orbit at a time. From those histories, scientists can separate short weather swings from deeper climate trends. In this window, you can also see another stabilizer, quieter than clouds, the ocean. Water stores heat efficiently, then releases it slowly, smoothing the difference between day and night and between seasons. Currents move that stored heat around the globe, carrying warmth toward colder regions, and returning cooler water toward the tropics. The Moon's influence reaches into that moving water through tides. The rise and fall you know on shores is the surface expression of the Moon tugging on the whole ocean. Tides stir shallow seas, mix coastal zones, and create rhythms that living things can use as a clock, a recurring pulse that has been present for a very long time. Over even longer time, tides also change the length of the day. Earth's spin slowly loses energy to the friction of moving water, and the Moon's orbit slowly expands as it gains that energy. The change is small each year, but over ancient spans it reshapes the tempo of daylight, like a metronome drifting from fast to steady. This shifting tempo ties back to climate in subtle ways. A faster spinning Earth would have had shorter days, different wind patterns, and different balances in how heat was transported. Scientists model these effects carefully, because they are intertwined with the changing positions of continents, the chemistry of the air, and the brightness of the sun long ago. The Moon also affects Earth's tilt, the angle that gives seasons their character. Earth's axis wobbles over time, and the gravitational pull of the moon helps keep that wobble from becoming extreme. Without a large companion, the tilt could vary more, which might lead to more dramatic swings in sunlight at high latitudes over long spans. Even with the moon, the tilt is not perfectly fixed. It shifts slightly, along with the shape of Earth's orbit, in cycles that help pace ice ages. These are natural variations, and they unfold slowly enough that glaciers have time to grow and retreat. From space, their traces appear as carved valleys, layered ice, and ancient shorelines. If the word ice age sounds sharp, you can soften it. It is not a single winter. It is a gentle rebalancing that takes many human lifetimes, driven by small changes in sunlight distribution. Earth is resilient through these cycles, and its oceans and atmosphere act like buffers, absorbing and releasing heat with patience. From the spacecraft, you also see how Earth is not only shaped by physics but by life. Plants and plankton change the chemistry of air and water, pulling carbon from the atmosphere and locking it into bodies and sediments. Over time, life helped build an oxygen-rich atmosphere, which in turn allowed complex animals to breathe and thrive. This connection between living things and the planet is called a biosphere, and from space it leaves faint signatures. Seasonal changes in greenness follow the swing of sunlight across continents. In certain colors, forests and crops reflect light in a way that bare rock does not. Even the composition of the air, measured by spectroscopy, carries the imprint of biology. You can imagine an even farther observer, looking at Earth as a point of light. They would not see oceans or clouds separately, only a combined brightness that varies as the planet rotates. Yet even in that light curve, there are clues: periodic dimming as land turns into view, subtle color changes as clouds gather, and a spectrum that hints at water and air. In a way, Earth and Moon together create a clearer signature than Earth alone. The Moon adds a second point of light, varying in brightness as it changes phase. If you watched from far away, you could detect that paired dance and infer an orbiting companion. That fact matters for how astronomers think about other potentially habitable worlds. The Moon also served as a calibration target for human instruments. Its surface is stable, and its reflectivity changes in predictable ways with phase and angle. By comparing satellite measurements against the Moon, engineers can check weather sensors drift over time, keeping Earth observations consistent across years and across different spacecraft. As you listen to the hum of the cabin, you can feel how much of modern Earth science is, at its heart, simply careful comparison. Compare today's sea level to last decade's. Compare this summer's Arctic ice to earlier summers. Compare the chemistry of the air at one latitude to another. The work is steady, not sensational. There is also a modern shift that scientists track with calm clarity: the strengthening of the greenhouse effect as humans add carbon dioxide and other gases to the air. The basic physics is well understood. The details, like how clouds and oceans respond, are still refined. But the direction of the energy balance is measurable from space. Even that topic can be held gently. From your window, Earth is not a problem to solve in one night. It is a home with feedbacks and buffers, and it responds to changes in ways that can be studied and, with care, guided. The point is not alarm in the dark, but awareness in the light of understanding. The Moon is a quiet partner in that awareness. Because it lacks weather and biology, it shows you what a rocky world looks like without those layers. Its craters persist. Its dust stays put. In that steadiness, it becomes a reference point, a contrasting mirror that helps you appreciate how active Earth truly is. Earth's activity includes plate tectonics, a slow conveyor of crust. Plates drift, collide, and sink, recycling carbon and shaping mountain ranges. This recycling helps regulate long-term climate by moving carbon between air, ocean, and rock. From space, you can see the surface expression in the lines of trenches, the arcs of islands, and the folds of ranges. The Moon, without that plate system, kept many of its earliest surfaces. That difference means the Moon can preserve the scars of the early solar system, while Earth keeps only scattered hints. When scientists want to understand how often big impacts happened long ago, they often read the Moon first, then translate with care back to Earth's erased record. Impacts connect to habitability in a quiet, complicated way. Too many large impacts too late could keep a planet hot and unstable. Too few impacts early could mean fewer deliveries of certain volatiles. Earth seems to have lived in a middle path, with enough early energy and materials to build oceans and chemistry, and enough later calm for life to persist. From this distance, it also becomes clear that habitability is not a single switch. It is a set of boundaries: temperature, pressure, chemistry, and time. Earth's distance from the Sun matters, but so do its atmosphere, its oceans, its magnetic field, its interior heat, and the steady presence of the Moon, shaping tides and stabilizing tilt. You might notice, as Earth turns, that the brightest regions are often clouds, not continents. That is why albedo is so important. A growing ice sheet makes a region brighter, reflecting more sunlight and cooling further in a feedback. A shrinking ice sheet exposes darker land or water, absorbing more sunlight and warming further. Earth's climate is full of such gentle loops. The ocean has loops as well. When seawater freezes, ice forms mostly from fresh water, leaving salt behind, which makes the remaining water denser. Dense water can sink and drive deep currents, connecting polar regions to the rest of the globe. These currents move slowly, on the scale of centuries, and yet they are part of the planet's steady heartbeat. The Moon has its own long loops, too. Its orbit is slightly tilted and slightly elliptical, and it slowly precesses, changing how its path is oriented in space. These motions modulate tides and affect how and when eclipses happen. They are small variations, but they are also reminders that even stable systems have layers of motion. From the spacecraft, the Moon's pale disk also reflects light onto Earth's night side. The effect is subtle, but it is real, a gentle brightening of nights on ocean and land. In human culture, that light became a guide for travel and timekeeping. In physics, it is a transfer of photons from Sun to Moon to Earth, a slow, steady exchange. Sometimes you can spot lightning flickers along Earth's limb, like tiny silent pulses inside cloud towers. They are brief and far away, and from here they feel more like texture than danger. Thunderstorms are part of the engine that moves heat and moisture, lifting warm air, releasing latent heat when water condenses, and feeding larger patterns. Even the color of Earth's oceans can tell you something calming about life. In certain seasons and regions, microscopic plankton bloom, changing reflectance in a way satellites can detect. Those blooms are not just pretty. They are part of the carbon cycle, drawing carbon into the ocean's living layer and, in some cases, sending it downward when organisms die. If you widen your mental view beyond Earth, you can see why astronomers care about these signatures. When they find planets around other stars, they often see only small dips in starlight or a faint spectrum. Learning Earth's combined signal, and how it varies with clouds, oceans, and seasons, helps them interpret those distant traces with humility and care. In that wider view, the Earth-Moon pair is also a reminder that planets can have companions that matter. Some exoplanets may have large moons, though they are hard to detect. If they exist, they could influence tides, tilt stability, and even the way a planet's day length evolves. The idea is not certainty, but possibility grounded in physics. Back in the cabin, the ship's instruments glow faintly, and you might imagine them logging the same basics: temperature, position, power, orientation. Spaceflight depends on steady housekeeping. So does science. So does a sleeping mind, which also keeps its own quiet records: breath, heartbeat, warmth under a blanket. As you keep watching, the Earth's terminator slides across the Pacific, and the Moon's crater rims slip into shadow. The darkness is not empty. It is simply the absence of reflected sunlight, a reminder that light is a traveling thing. It leaves the sun, crosses space, touches a surface, and then either returns or becomes heat. That simple travel of energy is the thread that connects everything you have been hearing: the warmth of oceans, the chill of polar craters, the glow of infrared leaving Earth, the pale shine of moonlight. It is all sunlight, rearranged by matter and motion. In the quiet, you can let that unity be soothing. In the next part, you will draw closer to the modern picture of the Earth-Moon system as it is measured today, and to the open questions that still invite gentle curiosity. For now, you can rest inside the steady rhythm of two worlds, one active and breathing, one still and remembering, both turning together under the same star. You are still tucked into the quiet cabin of the spacecraft, where the panels glow softly and the air feels clean and cool. In the window, Earth and the Moon share the same dark stage, turning with unhurried grace. Tonight your attention shifts from the past into the present, to the way these worlds are measured right now. Out here, seeing is not only looking. It is listening to tiny changes in motion, sorting faint colors of light, and timing signals so precisely that distance becomes a number you can trust. Modern space science is a kind of gentle accounting, where patience is the most important instrument, and where even a whisper of data can carry meaning. Around Earth, satellites move like a slow, layered choir. Some fly low and fast, some higher and steadier, each tuned to a different part of the planet's voice. They watch clouds in visible light, heat in infrared, moisture in microwave, and the chemistry of air in narrow spectral bands, building a portrait that never fully stops updating. From this window, Earth looks serene, but its energy balance is always in motion. Sunlight arrives, some is reflected, some is absorbed, and the planet glows back into space as heat. Instruments in orbit measure both sides of that exchange, because the difference between incoming and outgoing energy shapes everything from sea ice to storms. Those measurements are calm by design. A detector does not gasp at a cloud bank, it records brightness, angle, and wavelength. Over many orbits, averages settle into patterns, and patterns become trends. In this way, the planet's changing radiance is turned into a quiet, readable signal, like a slow pulse traced on paper. Other sensors focus on specific gases, separating them by the way they absorb light. Carbon dioxide, methane, and water vapor each leave their own subtle fingerprints in Earth's spectrum. The method is not dramatic. It is careful subtraction, like listening for one instrument in an orchestra, and learning how its volume rises and falls. Over the oceans, radar altimeters send pulses downward and listen for the echo. The return time reveals sea level, and the shape of the echo hints at waves and wind. Small changes, spread across wide basins, add up to shifts in currents and heat storage, which matter for weather and for the calm stability of climate. Gravity, too, is measured from space in ways that feel almost magical, though they are strictly physical. When ice melts or water moves through a continent's ground, mass shifts, and gravity shifts with it. Satellites can sense those changes through tiny alterations in their own spacing and speed, translating invisible movement into maps. All of this Earth watching is not separate from you. It is how people learn what the planet is doing while you sleep, how drought and flood are tracked, how forecasts improve, how the long story of air and water is kept in a consistent record. The view from space becomes a kind of shared memory for a civilization. Now, when you let your gaze slide to the Moon, you feel the contrast. There the weather does not rearrange the surface each week. The data changes more slowly, but modern instruments are no less attentive. Laser altimeters trace the Moon's shape with fine precision, turning craters and ridges into a detailed terrain model. Gravity mapping has also grown exquisitely sharp. By tracking a spacecraft's radio signal and how its orbit bends, scientists infer where the moon is slightly denser or slightly lighter beneath the surface. These maps reveal buried basin rings, dense fills beneath Maria, and subtle structures that help tell how the moon cooled and reorganized itself. One of the most intimate measurements is still the simplest to imagine: a laser pulse leaving Earth, touching a reflector on the moon, and returning. That round trip, timed with extreme care, reveals the distance between worlds and how it changes. It also exposes tiny wobbles in the moon's rotation, like a slow nod. From those wobbles, scientists infer what the moon is like inside. A rigid, perfectly solid body would respond differently than one with a fluid layer that can shift and lag. The evidence points toward a small core and at least some fluid behavior, a reminder that even a quiet world can have a hidden softness at its center. Seismology adds another sense. Apollo instruments once listened for moonquakes, and the signals rang on longer than earthquakes because the moon is dry and fractured. Today, researchers reanalyze those recordings with modern techniques, and they plan and design new seismometers to hear more, especially in places the Apollo network never reached. The moon also has an atmosphere of a sort, though it is far too thin to breathe. Atoms are knocked free from the surface by sunlight, micrometeorites, and charged particles, then hop along ballistic paths before settling again. For a time, sodium and other atoms can form a faint, extended tail, drifting away like a pale veil. Near the surface, dust behaves in ways that are still being studied. Sunlight and plasma can charge grains, and at the boundary between day and night the electric environment changes. Some observations suggest that dust may loft or shift under these forces, especially at sunrise and sunset, though the details remain uncertain and gently debated. At the poles, the questions become colder and sharper. Permanently shadowed craters can hold water ice, and orbiters search for it with neutrons, radar, and infrared signatures. Yet, ice can mean different textures and mixtures: pure patches, thin grains blended with soil, or molecules trapped in pores, each with different implications. One open question is how that ice arrived. Some may come from comet impacts, some from water-bearing meteorites, some from volcanic outgassing long ago, and some from reactions driven by the solar wind. The moon likely gathered its water through more than one pathway, and sorting those pathways is part of the modern mystery. Another open question is how mobile water is on the moon today. A molecule can be freed by sunlight, hop to a cooler place, stick for a while, then hop again. Over long time, such hopping could concentrate water into cold traps, a slow migration guided by temperature and shadow like a drifting snow held in a deep canyon. The moon's magnetic story adds its own quiet intrigue. There is no strong global field now, yet some rocks are magnetized, and certain regions show magnetic anomalies linked to bright surface swirls. How long the ancient dynamo lasted, and what powered it, are still active questions, because they touch the moon's internal heat and early history. You can feel how much the far side still invites direct study. Great basins there may have exposed deeper material, and the thicker crust keeps secrets about early cooling. Orbiters can suggest compositions, but nothing replaces a sample sealed, brought home, and measured in a lab where precision is almost a kind of meditation. Sample return is, in many ways, the quiet gold standard. A rock in a lab can be dated, its minerals separated, its isotopes measured again and again by different teams. Each new sample also helps calibrate crater counting, tightening the timeline of impacts across the solar system and clarifying whether bombardment was spiky or smooth. That timeline matters beyond the moon. If impact rates changed sharply, early Earth surface conditions may have swung in response, affecting oceans and the chemistry that led toward life. If impact rates declined more gradually, the early environment may have been steadier. The moon's scars are the best evidence we have for this chapter. There are also mysteries that live in the Earth-Moon partnership itself. Tidal friction depends on the shape of ocean basins, the depth of seas, and the arrangement of continents, all of which change over deep time. That means the Moon's outward drift and Earth's day lengthening are not perfectly smooth, but modulated by geology. Modern measurements make even those slow changes visible. Laser ranging tracks the Moon's recession, and geological records on Earth hint at ancient day lengths. Together they form a single story told in two languages, light pulses and layered rock. The agreement between them is soothing, like two clocks ticking in the same quiet room. The tools that connect these worlds are also part of the present story. Deep space antennas listen for faint signals, and atomic clocks provide timing stable enough to measure distance by the speed of light. Navigation is a gentle dance of prediction and correction, where a small burn now prevents a large mistake later. Even time itself needs a little care out here. Signals are adjusted for relativity, because clocks tick at slightly different rates depending on speed and gravity. These corrections are not philosophical. They are practical, and without them, navigation and ranging would drift. In spaceflight, the subtle truths of physics become everyday housekeeping. As you gaze out, you can hold a modern kind of Earthrise in your mind. Cameras return it often now, from many angles, but the feeling can still be quiet and fresh. Earth is a luminous sphere with weathered continents and moving cloud decks, and you can sense how much of its story is written in water. You might picture the entire Earth as a set of overlapping maps: heat, moisture, winds, vegetation, ice, pollution plumes, night lights. None of those maps is the whole planet, yet together they form a complex portrait. The calm skill of science is in learning which layers answer which questions, and when to combine them. The Moon's portrait has its own layers: topography, gravity, mineral maps, temperature at noon and midnight, hints of volatiles, subtle magnetic patches. These layers are quieter than Earth's, but they are no less rich. They show a world that cooled, cracked, and settled, then kept the record open for billions of years. And still, some of the biggest questions are not about maps at all, but about origin. Why do Earth and Moon match so closely in certain isotopes? How thoroughly did a giant impact mix vapor and melt? Did one impact do the job, or did several smaller ones build the Moon through repeated rings and mergers? The answers are still being shaped. The Moon's early timeline remains a living topic as well. When exactly did the magma ocean freeze? How long did volcanism persist, and why did it prefer the near side? How much heat-producing material was concentrated there, and was the distribution set by the impact, by later internal flow, or by both? Each option leaves slightly different traces. Even the question of lunar water reaches inward. How much water is locked inside the Moon's mantle minerals? Was the early Moon drier than Earth by a wide margin, or did it keep more volatiles than we once thought? These are not just curiosity questions. They inform how planets, in general, keep or lose the ingredients for habitability. Far beyond the practical, the Moon also offers a calmer frontier for astronomy. The far side is shielded from much of Earth's radio noise, creating a quiet place to listen for faint cosmic signals. Some researchers dream of radio telescopes there, tuned to the earliest light of the universe, when the first stars were still forming. From your seat, that dream does not feel like a race. It feels like an extension of listening, the same patient listening that turns a laser echo into a distance and a spectrum into a gas concentration. The Moon, by being quiet, makes quiet science possible, and quiet science fits well beside sleep. Inside the cabin, the ship's hum continues, and your attention can rest on how all of this knowledge is gathered without hurry. Earth and Moon do not change their basic relationship from night to night. They invite the long view, the view that returns again and again, refining itself like a smooth stone warmed in the hand. In the next part, you can drift closer to the human layer of this modern picture, not the headlines, but the gentle reasons people keep returning to the moon and keep watching Earth. Tonight, it is enough to know that the measurements are ongoing, and that the biggest discoveries often arrive as quieter clarity, not sudden surprise. You are still in the small spacecraft, where the lights stay low and the air feels comfortably cool. The gentle hum of instruments continues without change. Outside the window, Earth and the moon drift through the same field of stars, two familiar shapes that make the darkness feel calm instead of empty. Tonight the journey begins to settle, like dust falling in slow motion. You have traveled through origins and missions, through craters and clouds, through measurements made of light and time. Now you can let the facts soften at the edges, not fading away, but finding their quiet place in you. Earth turns with a slow confidence, bright with ocean and weather. The moon keeps its pale steadiness, holding sharp shadows where there is no air to blur the view. From here, the difference between them is gentle and clear. One world breathes and moves, the other remembers. You can picture sunlight leaving the sun and crossing the space around you. It touches Earth, scattering into blues and whites, warming water and land. It touches the moon, reflecting softly from dust and stone. The same light, meeting different materials, becomes two different kinds of beauty. Gravity is the other quiet thread. It holds your spacecraft in an invisible embrace, and it holds the Earth and moon together as a pair. It shapes tides and orbits without ever needing to shout. It is a steady rule that works the same in every direction you look. When you think of tides, you can imagine the oceans lifting and settling, a slow inhale and exhale along the coasts. The moon's pull is not a command, just a preference written into water. Earth answers by flexing, and in that flexing, energy is shared between spin and orbit. That sharing is why the moon slowly drifts outward, and why Earth's day lengthens by tiny amounts over long time. It is not something you feel from one night to the next. It is a deep rhythm, like the way a shoreline changes when you only visit after many seasons. The moon's surface carries time in a different way. Impacts arrive, carve a crater, and the crater stays, crisp and legible, because there is no rain to soften it. Regolith gathers, rays fade, and the record remains. The moon is a library where the pages are made of rock. Earth keeps fewer pages from its earliest chapters. Water and wind rewrite the surface. Plates drift, collide, and recycle crust back into the mantle. That restlessness is part of what makes Earth habitable, because it renews landscapes and helps balance carbon and heat over long time. From space, the atmosphere looks thin, almost like a faint glaze along Earth's edge. Yet it is thick enough to slow the loss of heat and hold liquid water on the surface. It is a fragile layer to carry the whole story of weather, climate, and breath. Satellites watch that layer in patient detail. They measure clouds and temperatures, winds and water vapor, and the quiet signatures of gases. They turn the planet into a set of gentle maps that update again and again, helping people understand a home that is always changing. Beside that living complexity, the moon offers stillness that is useful. Its surface is stable enough to calibrate instruments, and quiet enough to preserve delicate clues. Even its shadows, especially at the poles, keep secrets of cold that may hold water as ice, tucked away from sunlight. And still, some questions remain open in the best way. Scientists refine the story of the moon's birth, testing how a giant impact could mix material so thoroughly. They ask how long the moon's internal dynamo lasted, and how water moved, molecule by molecule, across cold and warm ground. These are not gaps that spoil the picture. They are spaces where the picture can breathe. In science, an open question is an invitation to look again with better tools, calmer patience, and deeper care. It is permission to be curious without rushing to be finished. To reach the knowledge you have been holding, people used simple tools and patient repetition. They aimed telescopes through unsteady air, listened to faint radio tones, and learned to trust the timing of a light pulse. Each method was a different way of asking the same universe to answer in its own language. Some answers came as photographs that widened the heart without changing the laws of physics. Some came as rocks in a glove, heavy even in low gravity, later opened in quiet laboratories. Some came as reflectors left on the moon, still returning laser echoes, still measuring distance with calm precision night after night. Other answers came from watching Earth itself, over and over, until patterns emerged. From above, clouds stop being local moods and become global shapes. Ice becomes a boundary line you can trace. The ocean becomes a moving store of heat. The view does not judge, it simply reveals what is already happening. Even the moon's familiar changes, crescent to full and back again, feel different when you remember the geometry. Half of the moon is always sunlit, and the phase is only the angle of your view. The clear explanation does not steal the softness of moonlight, it makes the softness feel earned. From far enough away, Earth and moon become a lesson in perspective. They remind you that most forces are gentle when seen across time, and that most changes are slow when seen across distance. The mind can follow that slowness and, without trying, begin to slow down too. From your seat, curiosity can be soft. You do not need to solve anything tonight. You can simply notice that knowledge has a texture, it arrives as images sharpen, as numbers gain meaning, as separate clues agree. It arrives like dawn, gradual and reliable. You might remember the first time humans saw Earth as a whole world from space, the curve of it against black. That view did not change the planet, but it changed the mind that looked. It made borders feel temporary and made the atmosphere look like what it is, a shared shelter. Even now, with many more images, the feeling can stay quiet and true. Earth is one bright place in a wide dark. The moon is one faithful companion, reflecting sunlight without heat of its own. Together they form a simple composition: light, shadow, motion, and time. If your eyes are closed, you can still picture the colors. The deep ocean blues. The white curls of cloud. The moon's gray plains and lighter highlands. The black between them, sprinkled with steady stars. The scene does not demand your attention, it offers it. Inside the spacecraft, everything remains steady. A soft fan moves air. A small indicator light pulses at a calm interval. The faint vibration of life support is a gentle reminder that you are safe, contained, and warm while the universe stays wide and quiet outside. You can let the idea of distance feel soothing rather than lonely. Space is not an emptiness that takes things away. It is a room that gives them space to be seen clearly. From far enough back, Earth and moon become simple forms, and simplicity can be restful. You can also let time feel slow in the same way. The moon's craters speak of ages too large for fear, and Earth's turning speaks of days that return reliably. Your own night is small inside these vast cycles, and that smallness can be comforting, like a quiet room inside a wide house. As the ship drifts, Earth's night side turns toward you, and you can imagine city lights under cloud. From this far away, they are not busy streets, just a soft glitter, like distant embers. They suggest human life without pulling you into its noise. Then the Terminator slides again, and dawn moves across a curve of ocean. The change is silent. Light arrives the way it always does, by traveling. Nothing rushes. Nothing strains. The slow geometry of orbit does all the work, while the ship's sensors quietly keep their steady watch. You can think of the moon's face, always nearly the same from Earth, and the slight wobble that lets you peek around the edges. The moon is stable, but not rigid. It has small motions, small flexing, small shifts, all part of being a real world, turning through space with patient precision. You can think of Earth's oceans as a memory of ancient heat, stored and moved, released and gathered again. You can think of clouds as the visible breath of water rising and falling. And you can think of the atmosphere as the thin boundary where the planet meets space. All of these thoughts can be held lightly, like smooth stones in your palm. You do not need to arrange them. You can simply feel their shapes: light, gravity, water, rock. If one slips away, that is fine. The universe does not ask you to carry more than you want to carry. If any detail feels too sharp, you can let it soften. You can return to the simplest view: Earth, blue and white. Moon, gray and calm. Stars, steady and distant. A small ship, quiet and warm, gliding without hurry through a dark that is not hostile, just vast. You might notice your breathing now, matching the ship's steady hum. Inhale, and the chest rises gently. Exhale, and it settles. The rhythm is yours, and it does not need to be forced. Like orbits, it works best when it is allowed to be natural, returning again and again without effort. Let your shoulders rest. Let your jaw unclench. Let the muscles around your eyes loosen, as if you are letting go of a squint you did not know you were holding. The body understands safety through small releases, one quiet signal at a time, and the bed answers by holding you up. In the window, Earth and Moon continue their slow dance, whether you watch them or not. You are allowed to stop watching. You are allowed to let the scene become background, like a familiar lullaby that continues even after you drift towards sleep, steady and uninsistent. The science you heard tonight is still true when you forget the words. Gravity will still pull, light will still travel, oceans will still rise and fall, and the moon will still keep its steady face toward home. Reality does not demand your attention to keep working. If your mind wanders, it can wander gently. It can circle back to one image: the thin blue rim of air, the bright curve of Earth, the quiet lunar gray. Or it can drift into nothing in particular, the way a cloud dissolves when the wind changes, until even the need for words grows faint. The ship's cabin remains dim, with a small constellation of indicator lights. The instruments do their calm work. The stars outside do theirs. You are held inside a soft pocket of warmth and air, like a small island of comfort floating in a dark sea. As you settle, you can imagine the spacecraft turning slightly, so the window frames the Earth and Moon together one more time. Not as a problem, not as a mission, just as a pair. A home world and a companion world, sharing the same sunlight, sharing the same night. You can let that pair become a simple thought: there is a place you belong, and there is a sky that holds it. The rest can fade. The details can wait for another night. Right now, you only need the quiet and the steady feeling of being carried, with the ship's hum as a small anchor. Inhale once more, slow and easy, as if you are drawing in the cool, clean air of the cabin. Exhale, and feel the bed support you, the weight of you sinking comfortably. Let the warmth of your blanket settle where it wants to settle. The universe outside is wide, but here, you are safe and still. Earth turns. The moon follows. The ship drifts on. And as the hum continues, you can let your thoughts dim gently, like lights being lowered. Nothing is required of you now except rest. Sleep can arrive in its own time, soft and unforced, while the window holds its quiet view in the dark.